Planet Earth is a thermodynamic paradox powered by fire and water, and it should not work. At its core, a nuclear furnace generates the heat to continuously build new rock. Around it, a global hydrosphere absorbs energy, redistributes pressure, and regulates friction. Fire creates, water controls. Physics suggests this combination should tear the planet apart, yet it hasn't. For over 4.5 billion years, the system has refused to settle into equilibrium. Within that narrow mechanical tolerance, a dependent layer emerged us. We are not inhabitants of a stable world. We are passengers riding inside a machine that survives only by remaining unstable. To understand how this system actually works, we must first strip away its camouflage and face what it has been hiding. That camouflage is the ocean. Remove the oceans, and the comforting image of the blue planet vanishes instantly. In its place, a virtual simulation reveals the planet's true face, a scarred, brutal topography that has been hidden under kilometers of water for eons. While the oceans cover 70% of the surface, nearly 90% of the seafloor remains unmapped by human eyes, a blind spot in our understanding of our own home. With the water gone, the Earth no longer looks like a sanctuary. It resembles a vast industrial chassis. We see the continental shelves not as beaches, but as the precarious edges of land masses extending hundreds of kilometers into the void. We see abyssal plains pockmarked by ancient violence and canyons that dwarf the Grand Canyon, carved not by wind, but by deep sea currents and turbidity flows. This is not a static landscape. It is forensic evidence. Every ridge, every trench, and every fracture is a record of the immense physical stress this planet endures every second. This drained model allows us to conduct a planetary-scale stress test. We are not just looking at rocks. We are observing the components of a thermal engine in motion. The mechanisms that built these features are driven by forces deep underground, specifically a heat source over 3,000 kilometers beneath our feet. This internal fire drives the chaotic movement of the crust, while the missing water acts as the counterforce weighing down the plates and regulating the temperature. To understand why the system hasn't failed yet, we must trace the energy to its source. And on Earth, that source is not at the surface, but deep beneath the ocean floor. We begin our inspection at the most prominent scar on the planet's face, a continuous fracture running through the center of the Atlantic Ocean. If this machine has been creating new rock for billions of years, it should have grown larger. It hasn't. According to the laws of conservation, matter cannot be created from nothing, nor can the planet simply inflate like a balloon without catastrophic structural failure. Yet the evidence of continuous creation is undeniable. Dominating the center of the drained Atlantic basin is a colossal geological feature, the Mid-Atlantic Ridge. While it looks like a mountain range structurally, it is a global expansion joint. It is one segment of a global mid-ocean ridge system that wraps 65,000 kilometers around the planet, the longest geological structure in the solar system. This is the seam where the planetary skin is ripped open and rebuilt. In Iceland, this seam rises above sea level, allowing us to stand directly inside the mechanism at Silfra. Here, the Eurasian and North American plates are pulling apart at a rate of approximately 2.5 centimeters per year. The rate sounds negligible, but over geological time, it becomes a relentless conveyor belt. This crustal separation is driven by mantle convection and decompression melting. As heat from the outer core radiates upward, it reduces the density of the semi-solid mantle rock, causing it to rise in buoyant plumes. As this hot rock approaches the crust, the sudden drop in pressure lowers its melting point, turning it into liquid magma. This magma injects itself into the fracture, solidifying to form new basaltic crust. It functions like a continuous hydraulic press, injecting molten basalt and forcing the plates apart. In physical terms, this is driven by buoyancy contrasts and pressure-dependent melting. Deep underwater, this heat exchange creates one of the most chemically hostile environments on Earth. Spaced along the ridges are hydrothermal vents, often called black smokers. These act as the system's chemical injection ports. Seawater seeps into the fractured crust, is superheated by the magma chamber to temperatures exceeding 360 degrees C, and then blasts back up into the freezing ocean. Because of the crushing pressure at this depth over 200 atmospheres, the water physically cannot boil. Instead, it becomes a supercritical fluid stripped of oxygen and heavily laden with dissolved minerals like gold, copper, and iron. When this superheated acidic fluid hits the cold seawater, the minerals instantly precipitate building chimneys that spew black metal sulfide smoke. In a stable system, this toxic, lightless, high-pressure zone should be a dead zone. Yet biology has infiltrated the machine. Among the vents, we find the scaly-foot snail, known to science as Chrysomalin squamiferum, a masterclass in evolutionary engineering. This organism does not merely survive the environment, it exploits it. The snail utilizes a biological process known as gene co-option, repurposing ancient genetic code to perform a radically new function, biomineralization of iron. It extracts the toxic iron sulfides from the vent fluids and synthesizes them into physical armor. Its shell is a tri-layered composite structure with the outer layer consisting of actual iron sulfide, specifically graphite and pyrite. It is the only known animal on Earth that grows a skeleton made of iron. This is not just adaptation, it is material optimization. The snail has effectively hacked the geothermal exhaust to build a suit of magnetic power armor. The presence of life here proves the system creates energy. But the mechanics of the ridge present a looming structural problem. The Earth generates approximately 2.5 square kilometers of new seafloor every year. The ridges push the plates apart, driving the continents into motion. But the planet's surface area is finite. If the Atlantic is widening, the Pacific must be shrinking. The new rock pushing out from the ridges must eventually go somewhere. The system cannot just keep building. To maintain its geometry, it must engage a far more violent protocol. The new skin must eventually die. If the Atlantic generator is pushing plates apart, logic dictates that somewhere else the crust must be disappearing. The Earth is a closed loop. It cannot expand indefinitely. To maintain its geometry, the system engages a recycling protocol known as subduction. This is the process where old, cold, and dense lithosphere is forced back into the mantle to be re-assimilated. The primary intake valves for this process are the deep ocean trenches surrounding the Pacific Rim. The Mariana Trench is the most extreme example, a depression in the crust nearly 11 kilometers deep. This is not merely a hole, it is a geological compactor. The physics driving this descent is density differentiation. As oceanic crust moves away from the ridge, it cools and contracts over millions of years, becoming denser than the underlying asthenosphere and the continental plate it collides with. Gravity takes over. The heavier oceanic slab loses buoyancy and begins to sink, pulling the rest of the plate behind it like a heavy chain sliding off a table. At the bottom of the Challenger Deep, the environmental stress reaches its peak. The water column exerts a pressure of nearly 1 Ru-86 bars, equivalent to over 1,000 atmospheres. At this density, the concept of biology as we know it changes. A standard human submarine would not just leak, it would suffer an instantaneous structural collapse, imploding as the air cavities inside were compressed to a fraction of their volume in milliseconds. Yet for the planetary machine, this pressure is necessary. It forces water-laden rock deep into the mantle, lowering the melting point of the material and fueling the volcanic arcs above. However, the descent of these massive tectonic slabs is rarely smooth. The interface where the two plates meet the subduction zone is not a lubricated surface. It is jagged rock grinding against jagged rock. This friction leads to a phenomenon known as stick-slip frictional instability. For centuries, the plates become locked together at high-friction contact points, called asperities. During this stick phase, the subducting plate continues to push, but the edge is stuck. This causes the crust to deform elastically, storing potential energy like a compressed spring, a process called interseismic loading. When the accumulated stress finally exceeds the frictional strength of the asperities, the system enters the slip phase. The rock snaps back to its original shape, releasing centuries of stored energy in seconds. We perceive this mechanical release as a megathrust earthquake. On March 11, 2011, off the coast of Japan, a segment of the Pacific Plate that had been loading stress for hundreds of years suddenly slipped. The release was catastrophic. The seafloor punched upward, displacing billions of tons of water and generating a tsunami that devastated the coastline. The energy release was so profound that it altered the planet's inertial metrics. NASA models estimate that the 2004 Sumatra Andaman earthquake, a similar subduction event, shortened the length of the day by approximately 2.68 microseconds and shifted the Earth's figure axis by about 7 centimeters. The energy release was sufficient to measurably alter the planet's rotation. These spasms reveal a critical vulnerability in our modern civilization. We have overlaid a delicate artificial nervous system, the global internet, onto this violent shifting skin. 99% of international data traffic travels through submarine fiber optic cables laid directly across these fault lines. These cables are strands of glass no thicker than a human hair, armored in steel and plastic. They are designed for a static world, not a dynamic one. In 2006, the Hengchun earthquake off Taiwan triggered an underwater landslide that severed 9 major cables instantly. The result was a systemic blackout internet traffic across Southeast Asia. Collapsed financial markets froze and digital communication networks went dark. We treat the ocean floor as a passive foundation, but in reality, we are running wires across the moving pistons of an engine. The cycle of creation at the ridges and destruction at the trenches keeps the crust in motion, but this grinding recycling process generates immense friction and heat. If the tectonic engine ran on rock alone, the friction would be insurmountable, and the subduction process would stall or melt the crust prematurely. A pure rock-on-rock machine would eventually seize up or succumb to thermal runaway. Without a fluid phase, friction increases, heat accumulates, and large-scale motion becomes mechanically unstable. To keep the conveyor belt moving smoothly for billions of years, the system requires a regulator, a substance capable of absorbing heat and modifying the viscosity of the rock itself. It needs a global coolant. Fire and rock explain how Earth moves. Water does not. Earth formed 4.5 billion years ago in the inner solar system, a region so hot that volatile compounds like water should have vaporized instantly. By all standard planetary formation models, the infant Earth should have been a dry, scorched rock, a sterile sibling to Venus. Yet we possess a global hydrosphere. 1.3 billion cubic kilometers of liquid water cover the surface. This massive volume of thermal buffer is too vast to be solely a byproduct of internal volcanic outgassing. If the machine didn't build its own coolant, it must have been imported. To trace the shipping manifest of this delivery, we must look back to the Hadean Eon, roughly 4 billion years ago. This was the era of the late heavy bombardment. The solar system was a chaotic shooting gallery. The migration of the gas giants Jupiter and Saturn disrupted the orbits of millions of icy bodies in the outer belts, slinging them inward toward the sun. Earth was the target. This was not a gentle hydration process. It was a kinetic injection. Comets and carbonaceous asteroids slammed into the primitive crust, delivering water not as liquid, but as ice and hydrated rock. This exogenous delivery hypothesis suggests that the oceans are in essence extraterrestrial debris. We are swimming in the melted remnants of a cosmic collision event. For decades, this was largely theoretical. To confirm it, we needed to examine the delivery trucks before they crashed. We needed a pristine sample of the early solar system untouched by Earth's biology or geology. Enter the OSIRIS-REx mission. Its target was Bennu, a near-Earth asteroid, and a fossil from the dawn of the solar system. The samples returned to Earth in late 2023 provided the physical evidence we lacked. The analysis of the Bennu regolith reveals that the water is locked within hydrated minerals, specifically phyllosilicates, commonly known as clays. This is the result of aqueous alteration, a chemical process in which liquid water interacts with anhydrous rock, incorporating hydroxyl ions or water molecules directly into the crystal lattice structure. This proves that the parent body of Bennu was not a dry rock but a hydrothermal system capable of sustaining liquid-water interactions inside its core. Crucially, recent analyses conducted in 2024 identified water-soluble magnesium-sodium phosphates in the sample. On Earth, these minerals are typically found in evaporation residues of soda lakes or in hydrothermal fluids. Their presence on a primitive asteroid represents a striking geochemical link. It suggests that the bodies bombarding early Earth were not merely delivering water, but also transporting specific chemical ingredients that form a prebiotic starter kit similar to those found today in the subsurface oceans of Enceladus. While the isotopic ratios of deuterium to hydrogen in Bennu do not perfectly match those of Earth's oceans, The mineralogical evidence confirms that C-type asteroids function as vast drifting reservoirs of volatile compounds. Once delivered, this alien fluid did not simply sit on the surface. It permeated the crust, creating a complex subterranean plumbing system. We can inspect this interaction at the Bahamas Blue Holes. These are not merely underwater caves, they are vertical shafts that cut through the geological eras, acting as access points to the planet's internal hydrology. Descending into a blue hole is like entering a chemical reactor. Near the surface, the water is fresh rainwater floating on top of the denser seawater below. But at a specific depth, divers encounter a visual anomaly, the halocline. This is the chemical interface. It appears as a shimmering false floor, like a mirror separating two bodies of water. Trapped at this boundary is often a concentrated layer of hydrogen sulfide, produced by bacterial decomposition of organic matter, that falls into the hole. The result is a highly toxic acidic barrier. Passing through it exposes divers to a chemically hostile boundary saturated with hydrogen sulfide. Below this toxic cloud, in the pitch-black, oxygen-deprived salt water, we find the remipedes. These blind centipede-like crustaceans are living fossils virtually unchanged for 300 million years. They do not belong to the surface world. They are residents of the dark fluid system, navigating a chemical environment that would be fatal to most surface life. Their existence proves that once water enters the planetary machine, it creates niches for life, even in the most hostile, isolated corners of the crust. But water does more than harbor life or cool the rock. It has mass, and it follows the laws of fluid dynamics. When billions of tons of water infiltrate the cracks of the lithosphere, the physics of the machine changes. Water creates pore pressure. It pushes back against the weight of the rock. In the geological engine, water stops acting just as a coolant and begins acting as a lubricant. And when you lubricate a system that relies on friction to stay stable, things begin to slide. In physical terms, increased pore pressure reduces effective normal stress, lowering frictional resistance within the rock. In the planetary machine, friction is what stabilizes motion. It keeps brake pads gripping rotors. It keeps tires on the road. In the planetary machine, friction keeps the massive ice sheets of Greenland and Antarctica anchored to the bedrock. Without friction, these continental-scale masses of ice weighing quadrillions of tons would slide uncontrollably into the ocean, raising sea levels catastrophically. For decades, we viewed glaciers as solid, slow-moving blocks that melted primarily from the surface down. This was a simplification. We failed to account for the plumbing. On the surface of the Greenland ice sheet, summer meltwater gathers into sapphire-blue rivers. These rivers do not flow to the sea. They disappear into gaping vertical shafts known as moulins. A moulin is a drain pipe drilled through kilometers of solid ice. It is the mechanism by which the surface connects to the base. When water plunges down these shafts, it carries immense kinetic energy, roaring like a jet engine as it falls. But the real work happens at the bottom, where the ice meets the rock. The physics governing this interaction is hydraulic jacking. Normally, the immense weight of the ice creates high friction against the bedrock. However, when pressurized water is injected into this interface, it exerts an upward force. If the water pressure exceeds the ice overburden pressure, it reduces the effective stress, which is the net force holding the ice in place. Essentially, the water lifts the glacier slightly off the rock. This increases basal transmissivity, the ability of the subglacial system to pass water, transforming a high-friction interface into a low-resistance sliding surface. Recent data from 2024 challenges the assumption that this system shuts down in winter. While surface melting stops, the subglacial drainage system can remain active, storing pressurized water in cavities. This means the lubrication effect is not just a seasonal anomaly, it is a persistent structural vulnerability. The water is actively greasing the gears of the cryosphere, accelerating the transport of ice into the ocean. But the water doesn't stop at the bedrock. Driven by gravity and pressure, it forces its way deeper, infiltrating the fractured crust itself. And where the water goes, the passengers follow. To see the absolute limit of this infiltration, we must descend into the Moab Kotsong mine in South Africa, one of the deepest excavations on Earth. Here, 3 kilometers below the surface, the rock reaches scorching temperatures of 60 degrees Celsius. This is the domain of the deep biosphere, a subterranean ecosystem completely disconnected from the sun. Miners and geologists here have tapped into pockets of fracture water that have been isolated for millions of years. This water is ancient saline and completely dark. By all surface logic, it should be sterile. It is not. In these hellish depths, scientists discovered Haliciphalobus mephisto, nicknamed the devil's worm. This nematode is not a microscopic bacterium. It is a complex, multicellular animal, thriving in an environment that should crush and cook it. This discovery rewrote the definition of the biosphere. These organisms are not living off sunlight or oxygen. They are powering their metabolism using hydrogen and sulfates generated by the radioactive decay of uranium in the surrounding rock. They are true insurgents occupying the deep fractures of the planetary machine, hacking a localized energy grid to survive. This proves that the alien injection water has thoroughly saturated the system. From the top of the glaciers to the deep crustal fractures, water has created a continuous connected medium. It links the atmosphere to the lithosphere, carrying energy, lubrication, and life into the very bones of the planet. We have completed the stress test. The results are clear. We do not live on a solid foundation. We live on a thin, fractured crust that is constantly being torn apart by internal fire, the planet's heat engine, and dissolved by external water, its global regulating system. The rigidity of the ground is an illusion. The stability of the climate is a temporary state. The system is currently balanced. The fire builds new rock. The water breaks it down. The friction holds the continents. The lubrication lets them slide. But this balance is not static. It is a dynamic equilibrium. It is a tightrope walk. And right now, the water-driven regulator is beginning to accelerate faster than the system was built to handle. The stress test is complete. The diagnostics reveal a truth that contradicts our most basic intuition. Safety is an illusion. We tend to think of Earth as a Goldilocks planet because it appears stable. The reality is the exact opposite. Earth is unique precisely because it is unstable. If the planet's internal heat engine had cooled down like Mars, the magnetic shield would collapse, the atmosphere would be stripped away, and surface water would freeze or vanish. If the external water system had boiled off like Venus, the crust would lock up, and the surface would be driven into runaway greenhouse conditions. Life exists only in the narrow, violent gap between these two extremes. We are the beneficiaries of a deadlock thriving in the friction zone where the heat of the core meets the chill of the void. This perpetual conflict, the building of mountains and the grinding of trenches, the injection of magma and the erosion of water, is not a flaw in the design. It is the engine of habitability. The system's refusal to settle into static equilibrium is the only reason we are here. But as passengers on this machine, we have begun to interfere with the controls. For millions of years, the two engines modulated each other on geological timescales. The rocks cycled carbon, the volcanoes replenished it. It was a slow, heavy rhythm. Now we are injecting energy into the water engine at a rate the fire engine cannot match. We are lubricating the glaciers and acidifying the oceans faster than the rock cycle can buffer. We are testing the machine's tolerances in real time. The Earth as a system is indifferent to the outcome. It has rearranged its surface before, and it will do so again. The machine will continue to run, driven by its nuclear heart and its solar skin, long after we are gone. The question is not whether the planet can survive the shift in balance. The question is, when the machine shifts gears to find a new equilibrium, can the passengers remain within its tolerances?